Hello everyone, welcome to the second half of our slideshow. I hope your brain has stopped hurting from the first half. Hopefully some PBS Spacetime videos will help as well. But we're going to move on to the next item, which is length contraction. Basically, as you go different speeds, length in the direction of travel also changes. So let me go through this example. We have a spacecraft. That spacecraft is traveling at velocity v away from the Earth. So if I am on Earth, as in diagram A, that spacecraft appears to be going at velocity v, and notice how it looks kind of short. If I'm in B, let's pretend that I'm the astronaut on the spacecraft. From my perspective, it is not me that gets shortened. I have my regular length because I'm in the same reference frame as the spacecraft. It has its normal length to me. However, it is the Earth and the Sun that appear flattened because from my perspective, they're the ones that are traveling away from me at v in the opposite direction. So notice how speed is relative to who you are. From the person on Earth, it's the spacecraft moving. From the spacecraft's perspective, the Earth is moving. And each of them, depending upon what the perspective is, something gets shrunk in the direction of travel. And that's length contraction. In fact, if I was on that spacecraft and I was going at the speed of light, the Earth would actually be flat. That's the only time it is flat for you crazy flat earthers. But when you are on the Earth is always a sphere or nearly a sphere. Now notice the equation length contraction also has that square root of 1 minus v squared over c squared factor, that relativity factor. If I am going about the same speed as you, L equals L naught. It's the same length. We're in the same reference frame, Newtonian mechanics apply. But if I'm going at a different speed, I have to add in that relativity factor. Let's look at an example. An astronaut using a meter stick that is at rest relative to a cylindrical spacecraft measures the length and diameter to be 82 meters long and 21 meters wide. The spacecraft is moving 0.95 c away from the Earth. What are the dimensions of the spacecraft as measured by an observer on Earth? So, I am now the observer on Earth, looking at that spacecraft. So the length that I observe is equal to its observed length, the length of its regular length, 1 meter. So L naught, or no, sorry, the length was 82 meters. So the length measured by the astronaut was 82 meters, so that's L naught, times the square root of 1 minus v squared, and it is moving at 0.95 c relative to me, divided by c, and I square that. So if I take 82 times that factor, times the relativity factor, I get 26 meters. So if that spacecraft was sitting on Earth with me, it would be 82 meters long. But since it's going at 0.95 times the speed of light, it appears to me to now only be 26 meters long. Now the diameter stays the same because it is only in the direction of travel that space is warped. And it literally is warped. You're seeing it differently from different reference frames. Like length, like space, time, relativity also affects momentum. And it does that because momentum has a velocity component, which is distance and time. And I've now shown you that distance and time are both affected, right? Velocity is distance over time. So momentum also has that relativistic factor, square root of 1 minus v squared over c squared. Notice from the graph, and this is very important, that as your speed increases, your relativity goes up by this hyperbolic function. You start and it's about the same, but notice at around 0.8 times the speed of light, the relativity, the momentum has now doubled. And if I was going the speed of light, that curve would go to infinity. So if you have mass and you are going at the speed of light, you have infinite momentum, which would mean it took infinite energy to get you going that fast. That's why light can go the speed of light, because it has no mass. But if you have mass, you'll never be able to go to the speed of light because you can never overcome the fact that you need infinite energy. And the same is true in reverse. If you happened to be going at the speed of light and you had mass, it would take all the energy in the universe to stop you. And it would be pretty painful too, because you would coming to a stop from going the speed of light might not be a fun thing. The point is, you can never go the speed of light if you have mass because of relativistic momentum. It would take all the energy in the universe to overcome that momentum. And as you go faster, there is an increase in your momentum. Let's look at an example. A particle accelerator is 3 kilometers long and accelerates electrons to a speed of 0.999999997 c, which is very close to the speed of light. You can do that because electrons have a very small mass. Find the magnitude of the relativistic momentum of that electron. Well, I add in momentum equals mass of an electron 9.11 times 10 to the negative 31 kilograms times velocity of that electron 0.999999997 c. But I divide it by the relativity factor, 1 minus all of that, c squared over c squared. When I do that, I get 1 times 10 to the negative 17th kilogram meters per second, which is a pretty small value. So we don't have to worry about that electron ending all life on Earth, which is what some people were afraid of from particle accelerators. And that is only because of relativity. If I take out the mv, the factor by which the relativistic momentum is greater than the momentum without it is 4 times 10 to the 4th. That's 40,000 times bigger. So because of relativity and the fact that that electron is going so fast, its momentum is 40,000 times fast or more than it would be if it were going at about the same speed as me. Thankfully, it has a small mass, so the overall momentum is not that great. So space-time speed affects momentum. Another thing that it affects, and I already alluded to this before, is energy. And this is where we get what a lot of people think was Einstein's equation, E equals mc squared, when in reality the equation is E equals mc squared over the square root of 1 minus v squared over c squared. If you are at rest, meaning not moving, which is impossible because you're always moving, but if you are at rest in the universe, then your energy would be mc squared. And this travels into many different aspects. Kinetic energy would be the energy that your total energy minus your rest energy, because if kinetic energy has to be your total energy minus your potential energy, which would be your rest energy. To find your kinetic energy, it's just mc squared times 1 over the square root of 1 minus v squared over c squared minus 1. So I take that E minus that E naught, and I can figure out what the kinetic energy of any particle is based upon its velocity. Now we normally call kinetic energy 1/2 mv squared. So if if your velocity was really slow, so let's put 0 in for velocity, right? We're going to get 1 over the square root of 1 minus 0, or 1. So 1 over the square root of 1 is 1. Minus 1 is 0. The kinetic energy, if you are at rest, is 0. So it works. It still gives you the right answer. It jives with Newtonian mechanics, and that's one of the requirements. But the point is, your speed also affects your energy, but it's not just your speed, it's your speed relative to other objects. One last thing is a little bit into the general theory of relativity. Let's talk a little bit about mass, but we're going to link this to energy. The sun radiates electromagnetic energy at a rate of 3.92 times 10 to the 26 watts. That's a lot of joules per second. What is the change in the sun's mass during each second that it radiates energy? And what about 75 years? How much of the sun's mass is lost in one human lifespan? Well, first of all, if delta E naught is mc squared, so I can do just the E naught, I can calculate the change in mass. The change in mass equals delta E naught over the speed of light squared. So I told you it was 3.92 times 10 to the 26 watts, or joules per second. So in 1 second, its mass is going to change 4.36 times 10 to the 9th kilograms. Now 4.36 times 10 to the 9th kilograms is per second. So let's make that times 75 years, which is 3.16 times 10 to the 7th seconds. And let's put that over the mass of the entire sun, 1.99 times 10 to the 30th kilograms. In 75 years, the sun loses 5.0 on a 5.0 times 10 to the negative 12th of its mass, which means it would take 10 to the 12th lifetimes for the sun to lose all of its mass. So yes, the sun loses like the island of Manhattan every second in mass, but relative to the total size of the sun, it's not that mass. It's not that much. And more importantly, mass and energy can be converted. And I wish I had a lot more time to go into this, because I want you to understand that mass and energy are basically the same thing. Mass is just one way that energy manifests itself. And if you go on in physics, I hope that you come to that understanding. So if we know that mass and energy are related, and one of the things that we do in physics a lot is we'll do like, okay, this spring has no mass, or this object is moving with no wind resistance. We always create these false environments. And I want you to know just how false they are. And relativity is one way to prove that these environments are kind of false. I have a spring, and that spring is unrestrained. And I assume it to be massless. And we did that when we were talking about springs to get 1/2 kx squared. It turns out that 1/2 kx squared is still true, but the proof is much more complex when you take into account the fact that the spring is not massless. But suppose that I stretch or compress that string. That would take energy. Is the mass of the spring still 0? If the mass has changed, is the mass change greater for stretching or compressing? Oh, I didn't mean to go on. Basically, yes, the mass of the spring has to change, because that energy has to come from somewhere. I have to either put energy in or take energy out. So the mass does change. Mass and energy can be interconverted. And that's assuming that that mass is alone in the universe. So even that question has assumptions built around it. Now, if you don't fully understand that, that's okay. What I want you to understand is that everything that we talk about in physics has assumptions underneath of it that we may or may not be aware of. That's the key there. Let's go back to the example that I started with, the relativistic addition of velocities. How fast is that ball going relative to the ground? Velocity, ball, ground. Now, if it's just going 8 and 15, that's not very big, because relative to the speed of light, that would be really small. But as those speeds get bigger, I have to do the v squared over c squared. And here, because it's relative to itself, we have a plus instead of a minus. So if you're adding vectors, adding velocities, normally I would say the velocity of the ball to the ground is equal to the velocity of the ball to the truck plus the velocity of the truck to the ground. And I would say, okay, that ball is going 23 meters per second. But if I know their velocities relative to the speed of light, relative to an observer, then I can actually make a more accurate answer by adding a 1 plus VBT VTG over c squared. Now, obviously, 8 times 15 is going to be really small relative to 800 million squared, which is c squared. So that basically that denominator becomes 1, and the velocity is 8 plus 15. But as it gets bigger, we actually have to also take into account. So the key here is, as your speed relative to something else is large enough, space and time are affected. So let's finish up. The cruiser is approaching a hostile spacecraft. The velocity of the cruiser relative to the spacecraft is 0.7 c. Both vehicles are moving at constant velocity. The cruiser fires a beam of laser light at the enemy. The velocity of the laser beam relative to the cruiser is positive c. What is the velocity of the laser beam relative to the hostile spacecraft? Well, what is the velocity of light? And what is the velocity, and at what velocity do the renegades aboard the hostile spacecraft see the laser beam move away from the cruiser? Well, the speed of light, as I told you, is a constant. So even if you change your reference frame, the speed of light will stay the same. So the velocity of the laser beam relative to the hostile spacecraft will still be positive c. However, from their perspective, it will not be moving at the speed of light away from the cruiser. It will be moving at the speed of light towards them. The cruiser is also moving at 0.7 times the speed of light towards them. So the light is moving at c towards them. The cruiser is moving at 0.7 c towards them. So it appears that the light is only moving 0.3 c away from the cruiser. So at what velocity do the renegades aboard the hostile spacecraft see the laser beam move away from the cruiser? They see the laser beam move at 0.3 c away from the cruiser. And they could actually use that to figure out that the cruiser was moving at 0.7 c relative to them, because light always goes at c.